Good morning. I'm happy to be present on the conference. I'm Milena Čukić, and I'm going to present you the work of our group, which is international. So let me start with my presentation. We basically did cross-section research in the field that we are active, which is computational and psychiatry application of nonlinear markers and machine learning. So we focus our research on depression because this is one of the biggest issues for work disability worldwide. More than 350 million of people are sick, and basically current practice in psychiatry is not using any objective tests, which we want to change. So we use some nonlinear measures, which are basically coming from complex dynamic systems theory. And in this research that we are comparing with others, we are using Higuchi fractal dimension with sample entropy, which you have some examples on screen. For example, fractal dimension on left of epileptic focus is showing below that fractal dimension drastically dropped during the onset. On the right hand side, you can see the difference between sick and healthy child when up entropy is actually calculated from their signal. So computational psychiatry is a successful marriage between computational neuroscience and psychiatry. The first idea, which is theory-driven computational psychiatry, is that we use some high definition imaging technique to have a structure and functionality of, for example, brain of other organs, then use other computational methods and do a kind of approach that we can use biomarkers extracted from that research for early recognition of diseases. But we are most opting for data-driven approach when we are just using low-dimensional data to do that, because MRI or techniques like this is simply too expensive to do every day. So we focus on EEG, which is basically the oldest neuroimaging technique, which exists almost 100 years. It is non-invasive. It is basically present in every modern hospital, and you can very easily and shortly record the signal from somebody's brain. So you can see from one of our research that the data are clearly separable. If you characterize that signal with nonlinear measures, which are more accurate than standard classical ones, you can describe more realistically the characteristics of human brain system or any complex dynamic system, because our systems are highly nonlinear, non-stationary, and noisy. So it is pretty hard to describe appropriately with classical measures. So this is part of our results. On the left, you can see that we characterize the data, meaning EEG of depressed and healthy people, with two nonlinear measures, and then use 7 most popular machine learning models, and all of them actually ended up in very high accuracy. On the right side, you can see that if you use PCA for feature selection, you can even with 1 PC or 2 or 3 already can solve a task in very successful way, but also you can use more if you want. On this slide, you can see the reason why we are advocating and actually suggesting to other fellow researchers to use all electrodes they recorded, because every electrode is contributing to the overall accuracy. And we noticed that some other researchers are using only 1 or 2 or 3 or 5 or 7 electrodes, explaining that with being it handy for clinicians to use, but we are against actually not using all of them. So very early on in our research, we realized that we cannot compare research due to very wide variety in methodologies applied. So we basically tried to discuss every single step of analysis. For example, how the signal was recorded, how it is pre-processed. We believe that unprocessed data are the most information rich, how artifacts are removed. For example, we opted to use epochs from the parts of the signal with minimum artifacts or without artifacts. Then time series analysis, feature extraction, feature selection, validation, and finally we compared accuracies of final classification. This is just a table of research we actually commented in this work, but I'm not going to spend some time here because you can read that in your materials. The most important problem is, for example, very modest samples. So majority of them are less than 50, and we advise higher samples to actually to improve the accuracy and realistic application of research, which can be done through several sites collaboration or using other people's already used recordings, etc. So Dutch initiatives are exemplary. For example, Amsterdam Centrum anonymized and digitalized a big number of their data, so they're accessible to collaboration. The central part here is generalization, whether generalization is realistic, and we are talking about overfitting or how to avoid that, and we are strongly advising internal and external validation, and especially contamination of the data, because contamination of the data and a modest sample are leading directly to algorithm optimism, which is basically the fear making fool of ourselves. This is one very straightforward explanation of the overfitting, because in our work we find out that the algorithm is basically trying to resemble the first data set that you present. And we are talking also about nuisance data. So we also recommend very often that people use more receiver operating curve, because this is the most efficient way how you can really see whether your accuracy is actually usable. And to conclude, we basically summarize our suggestions for our researchers. Firstly, we should standardize how the research is registered and what would be the threshold for accepting something for publication. If we do that, we will be having much more good quality studies, because majority of studies we examined actually are not reproducible because they are not reporting sufficient details so somebody else can do the same research. Then we are talking about machine learning as a piece of equipment. You have to learn how to use it, you have to learn how to calibrate it, how to avoid mistakes. And finally, we have to introduce all of that to our students very early on, because they really have to learn and have the idea about what is the practical usage of their knowledge. So thank you for listening, and I will be happy to answer your questions later. Thank you.